Ladies and gentlemen, now we still have one session of Keynote speech for first day on our international conference today. There will be Professor Imad, Moh'D, Rashid, Hamadneh from Material Chemistry, Department of Chemistry, Faculty of Science, University of Jordania, who are already joining and attending our international conference via Zoom. And on this session will be moderated by Head of Chemistry Education, University of Mataram, Dr. Saprizal Hadi Saputra. For Dr. Saprizal Hadi Saputra, time is yours.
Before the session comes, we would like to address once again Professor Imad. Welcome to second ICSES 2022.
Thank you.
For Dr. Saprizal, time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, selamat pagi, tetap semangat, the honorable speaker and all participants, ladies and gentlemen. I'm Saprizal Hadi Saputra, and I'm your moderator for this second session of the keynote talk. And for this second session, we have two honorable speakers. The first is Professor Imad Muhammad kHAIR Rashid Hamadneh from Jordan, and Dr. Muhammad Tirmizi bin Burhan from Malaysia. And the time given for this second session is about 15 minutes. So each speaker will be talks about 20 minutes. And then after that, we go for the question and answers. Okay, and you can ask questions directly in person like we did, and you also can chat, ask questions from the chat room in Zoom. So I would like to call Professor Imad Muhammad kHAIR. Hello, Professor.
Hello, assalamu alaikum, everybody. And good morning.
Okay, Professor, you the first. So I would like to, before you give your talk, I would like to read your short CV. Professor Imad Muhammad kHAIR Rashid Hamadneh. He was born in Damascus, Syria, and he finished his undergraduate in chemistry in the Moh'D University, Al-Kara, Jordan, and then he took his master's degree in chemistry. It was in 1999, University Kebangsaan Malaysia. He graduated from Malaysia for his master's degree, and he took his PhD in material science program from the same country, but different university, University Putra Malaysia. And Professor Imad research interest is in material chemistry. That's including ceramic, superconductor, nanocomposite material, biodegradable polymer, nanomaterial, and most of this work is in a biological active and antimicrobial and anti-cancer for those materials. So, Professor Imad, time is yours, please.
Thank you so much, Mr. Chairman, and good morning, everybody. The title of my presentation is effect of heat treatment on the formation and transport properties of gadolinium-based superconductor prepared via nano co-precipitated powders. I'm Imad Hamadneh from University of Jordan. And let's start talking about nanoparticles that are a group of atoms or molecules that having at least one-dimensional structure with a size range between 1 to 100 nanometer. And also several methods were used to prepare nanoparticles, either physical methods or what we call it top-down approach, or chemical methods starting from small atoms going to big molecules. We call it bottom-up approach, and the recently what they call it biogenic method, and is used not for a long time. But actually, we use this nanoparticles and synthesis of nanoparticles to produce superconductors that are materials show no resistance below a certain temperatures and can be characterized by two distinct effects: the zero electrical resistance at certain temperatures and exhibit perfect diamagnetism, which means expel the magnetic flux from its interior. Actually, superconductors prepared by several techniques, as we mentioned earlier. In physics, they use conventional solid-state route by mixing metal oxides, carbonates, metal salts, and pulverize it in powder form and calcine it or expose it to heat treatment until we get the final product. But as a chemist, we normally use a wet method, which includes sol gel, freeze dry, co-precipitation, that's what I will talk about today, and spray pyrolysis. The last four techniques are normally produce nanoparticles. Superconductors has unique applications such as high field magnets, squid sensors, plumeters for magnetic field, particle detectors. These are applications for basic research or in electronics, such as sensors, supercomputers, cryoelectronics components, and also in medical applications for in diagnosis, or such as squid, magnetic resonance image, and also in microwave techniques for telecommunications, such as filters, antenna, resonators, and delay lines. In also power engineering, such as electrical generators, motors, transformers, current limiters, switchers, and other active components. And finally, in traffic engineering, magnetic transport systems, ships engines, and maglev, and recently what they call it the hyperloop. These are examples for the applications. In this picture, we have a superconducting cable that consists of superconducting tapes. And if you want to know what is the tape, is the tiny material that they've been used, and it's carrying at least three times current more than the copper cable. Also, the supercomputers that been used recently. Also, this picture show the maglev train that been operated for research in Japan and in Germany. Superconducting motors for ships and current fault limiters. The objectives of this study is to synthesize the gadolinium-based superconductor, which is actually a 1-2-3 system, has an orthorhombic structure, which is perovskite material, of course, by using co-precipitation method at different centering temperatures. Then the characterization technique will be carried out to understand the system and try to know the physical and chemical behavior for the system, such as thermal gravimetric analysis, X-ray powder diffraction, scanning through microscope, and then where the electrical properties will be investigated. So in methodology, we will start normally by preparing the nano precursor, which is mixing the oxalic acid with gadolinium, barium, copper ion salts. Normally we use acetates, or we can use nitrates. We mix it in right proportion amounts. The ratios normally is 1 to 3 molar ratios with oxalic acid and forming a complex. This complex will be filtered and drying overnight, and then the dry powder will be tested for TGA and SCM. So after reaction or reacting the gadolinium, barium, and copper acetates with oxalic acid, so we will have highly homogenized mixture, and the precipitate will be in a sky blue color. That what will dry overnight, and next day we will do the thermogravimetric analysis in order to find out what is the correct temperature for heat treatment, calcination, and sintering. As you can see here, there is 5 drops, and these drops are summarized in table 1, showing the each drop and what is the chemical reaction occurring at that step. For example, dehydration occurred at step 1. In step 2, the water of crystallization will be removed, and in drop 3 and 4, the material will be converted to oxides and carbonates, and in final drop, the material will be converted into high temperature superconductor. So after that, we will continue the calcination, and based on the TGA thermogram, we found that the best temperature for calcination and sintering is above 900 degrees centigrade. So we do a calcination at 900 degrees centigrade for 12 hours, and then we cool down the system. We grind the material for 5 minutes. Then we press it into pellet form, and then subject it to heat treatment at 900 degrees, 920, 930, 940, and 950 for 15 hours. After that, the centered pellets will be subjected for characterization, XRD, STM, and resistivity measurements. So after the centering, the results showed that all the centered material has an orthorhombic structure and is a dominant phase. The phase of orthorhombic structure is the dominant. The material is perovskite structure and can be characterized by a match software, and the result was summarized in table 2. So by calculating the density of the percentage, sorry, for the material for using the X-ray data through the calculating the summation of intensities for the 1, 2, 3 phase divided by the whole intensities for the peaks, multiplying by 100%, we will get the average percentage for the phase that we are looking for. And also will be summarized in the table 2. So for the electrical behavior, all the materials showed the what we call it metallic behavior, and there is a sharp drop to zero resistance at temperatures ranged between 89 or 88 to 95 Kelvin. So based on that, we saw that as the centering temperature increases, the critical temperature will be decreased. So all this will be found also in table 3. But actually, we did something else. We managed to calculate the relative density and the porosity, and we found that the material getting higher relative density as the centering temperature increases, and same thing for the porosity, but in the opposite manner, that decrease in porosity as the centering temperature increases. So we managed to calculate the maximum current density for the materials that being produced as a function of centering temperature, and we found that the maximum current density increases as the centering temperature increases. And this measurements being done at 77 Kelvin. So we tried to explain what's going on. So we found that based on the increasing in centering temperature, we expect that the decomposition of the superconducting phase and having non-superconducting phase like gadolinium 211 phase, which is orthorhombic, and it acts actually as a flux spinning centers that enhances the critical current and critical current density as well. And based on the literature, we found that the centering or the what we call it the impurities from 6 to 13% that been added to the pure superconducting phase enhances the critical current density by forming the what we call it the flux spinning centers. Also the SEM showed for the green or the complex that we have nanoparticles actually that been formed by co-prestation method, and that's why we call it nano precursor. And the particle size range between 25 to sometimes 40 nanometers. But after heat treatment at 920, 930, 940, and 950, you can see the gaps and pores that presented in the pictures here. The SEM photos decreased as the centering temperature increases, which enhances the connectivity between the grains and reduces the weak links between the grains. I can now say that in the conclusion, that we are succeed in producing superconducting material using co-prestation method type GD123, using metal oxalate powders as a starting precursor. The centering temperature can play an important role in forming impurities that might act as flux spinning centers and thus enhances the transport properties. The variation in the centering temperatures play an important role in the formation of the impurities, and that enhances the transport properties for electrical and magnetic applications such as current fault limiters, superconducting cables, wires, and superconducting magnets. With that, I end my presentation. Thank you for your attention.
Thank you so much, Professor Imad. Okay, let's wait, Professor. We have one more keynote. Dr. Hamadneh. Hello.
Hello, yes.
Dr. Hamadneh.